Hi there, I stumbled over this intriguing thing on eBay, and since nobody wanted it, I got it really cheap. It is in a very nice wooden box and fairly big. It looks self-made but with considerable skill and care. It looks like the maker applied some protection stuff over the writing in India ink, and while it preserved the writing, over time that protection stuff is now plainly visible. The seller was one of those jumbo flea market type of shops selling everything under the sun, from knick-knack, typewriter, books, old valve radios and so on. No information on the origin of this box. Okay, part of the attraction for me was certainly the Roentgens per hour meter from 1952 in the lower left corner. Roentgen is an old unit of measurement for the exposure of X-rays and gamma rays. Exciting stuff. Of course, this box has nothing to do with rays, X or otherwise. The front plate shows actually a schematic of what it is. A bridge circuit to measure resistances. The meter is the circle in the middle. R1 corresponds to this selector switch here, and R2 to the one next to it, while R3 is represented by those 5 switches on the bottom row. And the unknown resistor is supposed to be connected to these 2 sockets. R1 and R2 select powers of 10, and faint pencil marks below the 5 switches for R3 show that these form a resistor decade, with the most left one selecting 100 kilo ohms, followed by 10K, 1K, 100 and finally 10 ohms on the right. So R3 can be adjusted between 0 and 999,990 ohms in steps of 10 ohm. Let's have a look inside. The front plate is held with 6 screws that go into metal brackets. Everything is on the back of the front plate, which is very convenient. The big black thing on the left is the meter. The brackets hold the meters, look very much self-made, but nothing wrong with that. There are still pencil marks visible for the component locations. All resistors are directly soldered to the switches. The resistors may be old carbon composite types, but then they are all marked with a red band, meaning ±2%. Not sure if those were ever available with such tight tolerances. Interestingly, they all have little vent holes like those shown on the far right. I have not seen resistors like that before, but if anyone has more information, please leave it in the comments. On the most left you see an example what the maker did in 2 instances where 10 ohm resistors are needed. Instead of using 10 ohm, these are 2 20 ohm in parallel, resulting in 10 ohms but with double the current carrying rating. One more thing, notice how the maker bent the leads after feeding them through the eye of the switch contact? This makes indeed a very good connection, but it will be almost impossible to get them back out for a replacement. Let's hope that isn't needed. You may have already spotted this white sticker on the inside of the front plate. This sticker is a mystery all by itself and strikes me as quite odd. P&H Electronics, Eastwood, £40. I searched on the internet for that company but did not find anything. If anybody knows more, please leave it in the comments. This may just be the price for the raw material of the front plate itself, but then £40 is a steep price, more so if this thing is from the 70s or 80s. And why would the maker leave the price tag on while drilling and assembling the switches? On the other hand, if this is the price for the whole unit, why put the price tag on the inside, and moreover bury it at the most crowded place of the whole assembly? There are plenty of better spaces to put it. A quick look at the meter and its circuit. There are some resistors soldered across the red button contact, and the meter itself has 2 anti-parallel diodes across to protect it from cross overloads. There is an interesting lever coming out of the meter, not connected to anything in this unit. This is what happens when I slowly move the lever at the back. It changes the scale of the meter. How cool is that? Obviously in the X-ray unit where this meter was originally used, this lever was mechanically linked to a range switch. I want to find out what type of meter this is, but the 2 resistors on the red buttons are in series with it, so for convenience I decided to temporarily desolder one of the wires connecting the meter to the button. I am using this calibrator from Times Electronic as a current source to send a current through the meter. The reading is in microamps. As I increase the current, the meter deflects. Full deflection to the right is at 25 microamps. Doing the same with reverse polarity shows that full left deflection is at minus 25 microamps. So the native meter range is plus minus 25 microamps. By the way, you don't need a fancy current calibrator, just a multimeter with microamp range wired in series with a meter and an adjustable resistor connected to a DC voltage source of a few volts. In this example, I use one of the decayed resistors of the unit itself for convenience and to have everything in the same shot, but an external variable resistor of 1 megohm would have worked just as well. Anyway, the BM235 confirms the 25 microamps within the steps available on the decayed resistor. While 25 microamps are flowing through the meter and deflecting it fully, I'm using the O1 XTM1041 to measure the voltage across the meter. It's 26.63 millivolts. So full deflection to either side means we are measuring plus minus 26.63 millivolts. And using Ohm's law, 26.63 millivolts divided by 25 microamps means internally the meter has a resistance of 1065 ohms. By the way, the sensitivity of analog meters is usually characterized using something called ohms per volt. The higher the better. It is easy to calculate that this meter has 40,000 ohms per volt, which is pretty high. It means if we added a series resistor of just under 39K, so that the total of the meter's internal and the series resistor add to 40K, the meter would have a full deflection when 1 volt is applied. The maker of this box used that method to add 2 ranges for the meter, selected by the red button. If the red button is not pressed, 2 resistors are connected in series with the meter. Adding all the resistor values plus the internal resistance of the meter, we have 68,065 ohms, and with 25 microamps that equates to about 1.7 volts. So normally the meter shows plus minus 1.7 volts, but when the red button is pressed, the 2 series resistors are short-circuited and the meter shows plus minus 26.6 millivolts. With the wire resoldered and the red button not pressed, I tested this by applying a variable voltage direct from a power supply across the meter. You can just make out the connection on the far right. The voltage is shown on the blue multimeter. It works exactly as the math predicted. With the meter itself out of the way, I explored the circuit further and found a few oddities. Starting with R2. The O1 is connected directly to R2. The knob is on the 10 position, but the meter shows open circuit. Switching to the 100 ohm position and the meter shows 10 ohms. Moving to 1000 and the meter shows 100 ohms. 10 to the power of 4 meaning 10,000 and the meter shows 1000. 10 to the power of 5 which is 100k and the meter shows 10k. 10 to the power of 6 or 1 meg and the meter shows 100k. And that's as far as the knob turns. These chicken head knobs, by the way, fit only in exactly one position, so it's not that this knob itself is offset on the axis. The switch may be wired wrongly or the legend is off by a factor of 10. R1 in position 10 shows nothing. Moving it to 100 and it still shows nothing. So R1 behaves different to R2 which showed 10 at position 100. Then the pattern resumes. 1000 shows 100, 10k shows 1k, 100k shows 10k, 1 meg shows 100k. R1 has the same problem as R2 with the addition that the 10 ohm is not there at all. I'm beginning to wonder how the maker ever operated this thing. All rotary switches have been firmly aligned to the front plate using their index pins that stick through matching holes in the front plate that are just visible to the right of each knob. This prevents the bodies of the switches from rotating. They fit only in the position they are in, and as I said, the knobs fit only in one position on the axis. With so much effort invested by the maker, I find it astonishing that the carefully drawn scales for all 5 switches that make R3 are so very badly aligned to the switch positions. The knobs often point right between 2 marked positions, making the reading difficult. Maybe you get used to it over time, but if that were my project, I would not keep it that way and redo the scale. Here are R1 and R2 from the inside. R2 is on the right. The 10 ohm position is very visible because that is implemented as 2 20 ohm resistors in parallel. If you look across to R1 on the left, the corresponding position of the switch is unused. Moreover, it was clearly never used, so the missing 10 ohm on R1 is by design. Neither switch shows any sign of any additional resistors that were ever soldered in to implement the 1 meg position shown on the front plate. Those were obviously left out by design as well. After all these investigations, I decided to draw up a schematic, and here it is. We have R1 and R2 as they really are, with a missing 10 ohms for R1 and no 1 meg ohm for either. Next to the instrument is the already familiar range button to increase sensitivity by shortening the 2 series resistors. On the far right is the power socket with a switch to turn power on or off. And of course on the left we have the 5 decade switches that make up R3. Note that R3 has been given its own set of sockets. If no power is connected or the switch is open and nothing is plugged into Rx, this allows using R3 as a normal resistance decade switch in other circuits, which is a nice bonus feature. The main purpose of the whole thing is to measure unknown resistors plugged into Rx by adjusting R1, R2 and R3. Essentially we have 2 voltage dividers here. The first one is formed by R2 and R3 and the second one by R1 and Rx. The instrument sits in the middle, bridging the 2 divider center points. If the dividers do not produce the same voltage, the instrument will show a deflection to either side. If both dividers produce the exact same voltage, the delta voltage between them is 0 and the needle will stay in the center of the instrument. At this state, the bridge is called balanced. This circuit is called the Wheatstone bridge, although it turns out he did not invent it. I'm using a comparatively simple way to explain how it measures an unknown resistor Rx by assuming the bridge is already balanced. This means the left and right divider produce the same voltage, and so the delta between them is 0. It would be a fair bit more complicated to calculate the general case of the unbalanced bridge, because then you would have to consider current flow through the resistance of the meter in the middle as well. But in the balanced case, there is no voltage difference and therefore no current flowing through the meter. No current through the middle also means that the currents I2 and I3 are necessarily identical, and the same is true for currents I1 and Ix. But of course, the currents on the left and right part of the bridge can be very different from each other. Because the bridge is balanced, it further means that the ratio between the voltage across R2, called V2, and the voltage across R3, called V3, is the same as the ratio of V1 and Vx on the other side. If that was not the case, there would be a delta voltage. Now a bit of math. Using Ohm's law, it's possible to substitute the voltages in this equation by current times resistance for each case. Since the current I2 and I3 are the same and I1 and Ix are also the same, they can be eliminated from the equation because identical multipliers in the numerator and denominator cancel each other out. Last bit is to solve for Rx, and you end up with this neat formula, a thing of beauty and joy forever. It may be neat, but what does it mean? If you make R1 and R2 have the same value, they cancel each other, and Rx is then equal to R3 when the bridge balances. That is the easy way to measure resistances. But we can do more. The ratio of R1 and R2 provides a scaling factor for R3. I listed some of the cases in the table here. The column on the right shows what Rx would be if R3 had the value of 1, 2, 3, 4, 5, taking into account that R3 is set in 10 ohm increments. In the R1 equals R2 case, the scaling is 1 and Rx would be 123,450 ohms. You would make R2 greater than R1 to measure resistors with higher resolution than R3 provides. A factor of 1/10 allows measuring to 1 ohm, a factor of 1/100th increases this to 0.1 ohm. Of course, shifting R3 to ohms or fractions of ohms means you lose digits on the left. In other words, the price is a reduced range. To measure resistors that have a higher value than R3, you would make R1 greater than R2. A factor of 10 allows measuring up to 10 meg ohm. A factor of 100 would make it go to 100 meg ohms. Of course, In this case, you lose resolution, that is, digits on the right, in doing so. You may have noticed that in all cases the supply voltage does not even appear in the formula, and it's true that measurements are independent from supply voltage or its stability, which is a great plus. Yet it's a fact that a bridge works better the higher the supply voltage is, because the same small resistance imbalance causes a bigger and easier to spot delta voltage the higher the supply voltage is. But sadly, it is necessary to carefully control the supply voltage on a case-by-case basis, and the reason is to not overload the bridge resistors. The resistors look fairly beefy, but with precision resistors you do not want to load them to the limit, or they may permanently change their value. I assume these resistors are 0.5 watt types and can be safely loaded to half of that. It is fairly complex to come up with rules that avoid overloading resistors with a too high supply voltage. The most critical range is when fairly low resistances are involved, for example here, where the supply must not exceed 3.5 volts, while R3 is in the 10 ohms range. It is so complicated because in different scenarios, different resistors are becoming the limiting factor. This table is the simplest way I found to express this problem. Of course, it's only valid for this particular bridge. If consulting the table sounds like too much work, choosing the lowest safe voltage and using it for everything is a possibility, but it will make it difficult to measure some resistors with decent accuracy. And finally, obviously, this table assumes never to select 0 ohms for R3, which is possible, but put R2 at risk. After so much theory, some practical examples. Before starting, I had to address the wrong labels on R1 and R2 and the bad alignment on R3. It was driving me nuts. Since I did not want to mess around with the original, I simply designed and printed a paper overlay that fits over the parts that need changing. I laminated it so it's a bit more lasting. What a joy to finally have knobs that point to the right number. It may not always appear so depending on the camera viewing angle, but for the user it certainly is. I do my own front plates using the same method, and I made a video dedicated to that process. I have put a resistor in as Rx, it's just above the meter. R1 and R2 are set to 1K, which means 1:1 ratio, and therefore R3 should be giving the results in ohms directly. I put R3 at 901K to start with. The extra K is to avoid accidentally setting R3 to 0. Supply voltage is 5 volts. Turning the unit on, and it shows that R3 is way too high. Lowering the 100K to 0 does not help, and neither does the 10K. The 1K knob finally does reduce the meter deflection. 5K is too high and 4K too low, leaving it at 4K and adding resistance in 100 ohm steps. Using the red button, 600 ohm is still too low and 700 too high, so back to 600, and adding 10 ohm steps. I find it easier to detect needle movement if I keep cycling the button on and off. There's no more movement that I can see at 50 ohms, so the result is 4650 ohms for Rx. And the BM869S confirms that this is pretty close, 4641 something ohm. Not bad, but how about using 1/10th mode to squeeze another digit out of the bridge? I have a few choices. Let's try leaving R1 at 1K and increasing R2 to 10K. My table says I can now increase the supply voltage to 15 volts, which I did. I also preset R3 by shifting the value one digit to the left, so 40K, which corresponds to 4K of Rx. This will speed up the surge. Turning the power on, 40K is now too low as expected, and 50K of course too high. The 1K knob now needs to be at 6, which is again as I expected. It's getting tricky, but yes, 500 ohms seems a little too high and 400 ohms a little too low. But honestly, it's very hard to see any change moving the 10 ohm knob. I now have a reading of 4644 ohm, but the last digit is not very certain. In hindsight, a different 1/10th mode that allowed a higher supply voltage would have been a better choice. a different resistor, and back to 5V supply. R1 and R2 are set to 1K, so we are in ×1 mode. R3 is preset to 900.1K, the 100 ohms are again for safety, not to end up with 0 R3 accidentally. Pressing the button and R3 at 900K is still too low. Rx is obviously higher than R3. The solution is to try ×10 mode and increase the supply to 15V. Pressing the button shows that R3 of 9 meg is now too high, 2 meg is too low, and 3 meg just a little too low. Adding 300K seems about balancing the bridge, so Rx would be 3.3 meg ohm. Okay, a little off as the multimeter says it's 3.17 meg. One more resistor? The last one, I promise. I forgot to start the camera, so I missed recording the ×1 mode, which was not much other than Rx had to be between 40 and 50 ohms. That's why the last knob of R3 is still on the 50. This is the attempt to get a further digit by using 1/10 mode. All this is at 3.5V supply voltage. This tells us Rx is somewhere between 46 and 47 ohms. Trying to do better, I preset the decade for 100th mode and increase R2 to 10K. Turning the unit on, a little too low. It looks at 40 ohms, the bridge is balanced, so the complete reading for Rx is 46.4 ohm. The BM869S says 46.51, which is pretty close. I already mentioned that R3 is accessible, and if no power is plugged in and no Rx connected, it is a perfectly usable resistor decade. Here I am setting it to 1, 2, 3, 4, 5. Well, in an ideal world, this should read 123.45K, but the multimeter has its tolerances and the decade itself, of course, too. I did measure the accuracy of R3, and considering it's made of resistors of 2% tolerance, it's not too bad. The 10 and 100 ohm switches are worse than the rest, but even those are better than 2%, so nothing to complain. And equally important for the bridge is the accuracy of R1 and R2, which follows the same pattern, with R1 being generally a little better than R2. For bridge accuracy, what matters is actually the ratio of R1 to R2. I calculated those for the different combinations, and the result is the graph on the right. Those marked ratios are those with the lowest error. I leave you with a bit of video footage of the wooden box that houses the unit. I do admire the craftsmanship of making such a nice box. I can't imagine how much time and effort went into this whole project. And what should I do with this whole thing? For sure I won't be using the bridge for making resistance measurements. Using R3 as a decade is an option, but it's rather bulky for that, and I have better and smaller decades already. Any suggestions are welcome, please leave them in the comments. If you like my videos, don't forget to subscribe if you not have already, and maybe consider becoming a Patreon. That would really help this channel. The link is in the description. As a Patreon you always get early access to videos, a blog and other exclusive content. Thanks for watching.